Hi, this is Blah here. I'm doing chapter 3, 3.4, and my CYU is on communication 1 and communication 3. Let's get right into it. Okay, so C1. Changes in concavity can occur only at points of inflection. Is this statement true or false? Explain. So this statement is true because a point of inflection is where the graph of a function changes concavity from concave up and concave down. So this is concave up and this is concave down. Okay. If a function changes from concave up to concave down or vice versa, that's changing concavity. So don't mind my thing. Here, I'm gonna just make it straight. I'm not good with this here. So if it's like this, right? And we say this is 2. No, that looks bad. So we would say the change in inflection happens at 2 right here. Let me just erase this and put it in the middle. So you see, this is where it changes signs. And change in concavity must happen at a point of inflection, see? Point of inflection. And this is where the second derivative changes sign from positive to negative or negative to positive. So negative to positive, I'll show you guys. So if it goes like so let's get that out of the way. But not all places where the second derivative is 0 are points of inflection. The sign has to actually change. Okay, let's show that. Okay, I have an example. So if it's fx, right? By the way, don't forget this is second derivative. Okay, equals x3. So first we find the first derivative. That's gonna equal 3x2. Then we find the second derivative. That's gonna equal 6x. So here is 0. So we'll do concave up. And then x less than 0. We'll do concave down. And this explains this part right here. Because this is less, so that means it's negative. See, positive to negative, or negative to positive, it's less than 0, so it means it's in the negative right here. But not all the places where the second derivative is 0 are points of inflection. Here, I'll draw this graph right here. So this would go approximately. So this would be, let's say, right. Don't mind the graph. I'm not good with this computer stuff. So okay, so you see is no, that still looks bad. I'm trying to show like an accurate one. Okay, after many tries, we could see it changes right here at 0. And let's put f derivative x. Here is the POI, point of inflection, is at 0. So we could see it's concave down when it's less than x. We could see it's concave up when it's x like higher than. So that means positive, so it's concave up. So this proves the POI when the function changes concavity from concave up to concave down. Alright, on to the next question. Okay, we're on the next question now. And explain the conditions under which a rational function would have no vertical asymptote. So, a rational function has no vertical asymptotes if the denominator never equals 0 for any real number. Okay, and I'll show you. Okay, so I'll do example right here. So this is our thing. So explain the conditions under which a rational function would have no vertical asymptote. So this would have no vertical asymptote right here. And why? Because there is no vertical asymptotes if the denominator never equals 0 for any real number. Okay? This is x2 plus 1, 1. So this has to be greater or equal to x2 plus 1. So we know that vertical asymptotes occurs at x values. At values of x where it equals 0 and the function is undefined. The function is defined here. And also, to not have any vertical asymptotes, the denominator must never be 0. So that means it has to be like, so say it's qx. See, so this must never be 0. Okay, so this happens if the denominator has no real roots, or it's a constant, or has a complex root only. So to break it down, a rational function has no vertical asymptotes when the denominator never equals 0 for any values of x. This means the function is defined anywhere, not anywhere, everywhere. So there's nothing that makes it blow up to infinity. So the graph of this is going to look like this. Sorry if the graph is bad. So you see here. So for this function, sorry about this. Just fix this. Make this more down. Please don't take marks because of the graph. Just not go with this. So this function fx equals 1 over x2 plus 1 never has a vertical asymptote because the denominator is never equal to 0. See? So for this would equal to 0. X equals 5. And then we would put here x. See right here? We would put this right here if it equals to 0. So that's why the graph is smooth and doesn't shoot off. Here because see, it's just shooting off. So that's it for my video. Thank you guys for watching and have a good day.